Hello and welcome back to yet another session in the Google Gemini series. So this session is all about RAG, Retrieval Augmented Generation. I'm going to start with the basics of RAG and then walk you through two demos where we basically convert an existing PDF into embeddings and store that in Vertex AI Vector Search. And the second part of the demo where I use that vector store to perform retrieval and implement RAG. So let's get started. I want you to know 5 things about RAG before we get to the details. Number 1, RAG is used to enhance LLMs with external data. So RAG is all about feeding the LLM with external data that is already containing factual, accurate, and correct data. And this leads to the second point where it results in the increase in accuracy of the LLM response because the LLM has facts embedded within the same prompt, and that is what is called as context. It is going to come back with accurate responses. Third thing, it reduces training costs, model training costs, because you have 2 techniques to make sure LLMs don't hallucinate, where hallucination is a process where LLMs come back with content that is not factually correct. So to avoid that, there are 2 techniques. One is fine-tuning, where you need to build your own data set. You need very, very powerful infrastructure to train or fine-tune the model. And the second technique is what we are talking about, which is RAG. RAG is definitely much cheaper and easy to implement than fine-tuning or pre-training the model. So RAG has 2 phases. The first one is called the retrieval, which is a combination of 2 things. One is an embedding model that is going to take the existing data and turn that into embeddings. The second component is a vector database that is responsible for performing a semantic search. And then we have the second component of the RAG process, which is generation. So generation is the LLM that is taking the context provided by the vector database and then coming back with the accurate response. Ultimately, RAG is designed to improve trust and control through grounded data. So instead of letting the LLM decide what it wants to respond with, sometimes which may be inaccurate, we are basically grounding the LLM with the data that it needs to come back with factually correct data. So that is what is RAG all about. Now, taking a closer look at the number of steps. Again, there are 5 steps. The first step is the prompt, which is typically given by the user. Now, for a while, imagine you're an employee that's just joined, you're a new employee, and you're understanding the policies of an organization. So you're going to ask a chatbot on what is the annual leave policy. Now, this prompt is immediately sent to a search and retrieval component, which is going to perform a semantic search in the existing vector database, which already has vectorized and embeddings based on the company leave policy, PDFs or documents or web pages. So that is the second step, which is the contextual search. Now, once the contextual search is done, it comes back with some chunks of text or sentences, which actually contains the leave policy. Now, that is going to be injected into the prompt, and this process is called the prompt augmentation. So you have the prompt, and just above or just below the prompt, you have the context, which is the output from the second step, which is the contextual search. And now the prompt plus the context are sent to the LLM, and the LLM has all the facts that it needs to come back with an accurate response. Now, this step is called inference. So the chatbot is going to perform an inference on the LLM by sending both the prompt and the context. And the last step is the simple response that is coming back from the LLM, which is passed on to the end user. So these are the 5 steps involved in implementing RAG. So in this tutorial, I'm going to use Vertex AI Vector Search as the vector database, and we will use one of the models offered by Vertex AI Model Garden for converting the data to text embeddings. And then finally, we'll use Gemini as the the generation component, which is the LLM. So let's get to the demo. The first part of the demo where we take an existing PDF, convert that into embeddings and store that in Vertex AI Vector Search. So let's switch to the demo. All right, I want to build the case for this demo, the scenario for this demo. So we have a fictitious company called Lakeside Bicycles, and here is the employee handbook. Now, this employee handbook is tremendously helpful for any new employee who is joining the organization. But our goal as Gen AI consultants is to build a chatbot that interfaces against the employee handbook. So the new employee doesn't need to read the entire document. Instead, they can interact with this PDF and ask questions as if they are talking to a HR person or an individual. So by the end of this demo, we will build a chatbot that is capable of answering questions based on this document. So let's see what are the steps involved. Now, our goal initially, the very first step, is to take this PDF and convert this into a set of embeddings. That is the first step. Let's call that as step 1A. So step 1B is storing that in a vector database. And then the last step is basically using the vector database to retrieve the actual results. So let's switch to the demo, and I want to show you how we can basically convert this into embeddings and store it in the Vertex AI Vector Search database. So we are first going to import a set of modules. You will notice I'm using Google Cloud Storage and Vertex AI language models, text embedding model. And of course, we are using AI platform because this module gives us access to the Vertex AI Vector Search. This gives us access to the Gemini model, and this gives us access to Google Cloud Storage bucket. And we also need PyPDF2 because we want to load the PDF and create chunks out of it. We are choosing embeddings by sentence, so PyPDF2 will really help us with that. And then there are a set of imports that are required for housekeeping, like accessing the environment variables and generating UUIDs and so on. So once we import these modules, let's initialize a set of variables. Now, these variables will help us throughout this project. So I'm getting my GCP project from the OS environment variable that's already set. And then my location, the region is set to US Central 1, and then the PDF path, which is this, and it's called the Lakeside Handbook.pdf. And we want to create a bucket called Lakeside Content. The embeddings file is going to be called as Lakeside Embeddings.json. Sentence file, we'll split the sentence and we'll store that in a different file called Lakeside Sentences. And finally, the Vertex AI Vector Search index is going to be called as Lakeside Index. So we'll initialize these variables, and then we'll get to creating some helper functions. So the first helper function that we're going to create is extract sentences from PDF. Now, this is a very, very important function. What it does is it basically accepts a PDF as an input. And in our case, this is the PDF. And it basically uses PyPDF2 to read the file. And it extracts every sentence. So it looks for the delimiter, which is either the new line or the period. And then it converts the entire document into a set of sentences and returns those sentences. Pretty straightforward. And once we have those sentences, we need to generate embeddings. Now, every sentence is going to be passed through an embeddings model, and that returns in a vector. Now, this is a very important step. This is how we convert sentences, which are characters and strings, into a set of numbers, which are called vectors, while preserving their semantic meaning and the actual context. So this is a very important step. And here what we do is we take the sentence and we pass it through what is called as text embedding gecko. Now, this is an embedding model available within the Vertex AI model garden. So we will run this. And then what we need to do is we need another helper function, which will basically invoke the generate text embeddings, but it does two things. One, it for every new sentence that it finds, it's going to generate a UUID. And then it is going to save the UUID, which is the unique identifier for each sentence, and the actual sentence in a file, in a different file. And then it also saves the embeddings in a different file. So this helper function is really powerful in a sense that it accepts the PDF. It first extracts the sentences, and then it generates the embeddings for each sentence, and then it saves the sentences with the corresponding ID. It saves the embeddings with the same corresponding ID, and it basically enables us to do the next step, which is uploading the embeddings into Google Cloud Storage. So that's the next helper function, which is upload file. It basically takes a bucket name, the file path, and it basically uploads this entire file, the embeddings file that we're going to create, to Google Cloud Storage. And once we have all of this in place, the next step is to create the vector index. So vector index is the database responsible for storing all the embeddings that we generated. So this has three steps. Number one, you need to create an index. And when you're creating an index, you're pointing to the bucket which has got the actual embeddings.json file. And then you also give the dimensions, and this dimension is determined by the model. Because we are using text embedding Gecko, the dimension is 768. And then approximate neighbor count is 10. Now this decides how it basically indexes and how it retrieves when you perform a semantic search. So once you create an index, then you got to create an endpoint, and the endpoint is responsible for the interaction. Think of that as the API endpoint, where you can perform CRUD operations, you can retrieve data, you can update, and so on. And once you create the endpoint, you got to deploy it. So to keep this simple, for the index, the endpoint, and the endpoint deployment, we are using the same index name. That's it. Now, those are the helper functions, which will basically help us do these two steps. Number one, generate embeddings and upload it to the GCS bucket. Number two, create the vector search index based on that. So let's go ahead and run the first step. So now this is going to basically generate the actual embeddings. Now let me run this. Now what this comes back with, okay, my file path upload file, and okay, I need to fix this bucket name and file path. Okay, this got to be sentence file path. But guess what? I'm actually not going to do this because I've already created. So I'm going to use this, but I'm going to comment it out. Now, when this is done, we basically have the so when we actually generate these embeddings and the sentences, it comes to something like this. So let me show you. Yeah. So we have the ID, which is the UUID that is generated, and then we have the same UUID, but the sentence here is the same, but we have the embedding representation here. So basically the idea is we are going to upload the embeddings file to GCS and then use it to implement the vector search index and use this as the lookup. So when we perform a search, it basically comes back with these IDs. And when we want to really retrieve the corresponding sentences, we take these IDs, look up in this file, and retrieve the sentences. So these two files are very important. The reason why we don't want to include sentences in this is it will overwhelm the vector database. We don't need to really store. All we need is retrieving the IDs, and we can always look up those IDs in the local file and basically retrieve the appropriate sentences. This is okay because we have a smaller PDF, but if you have a large PDF or a long set of files, you might prefer the other way. But to keep this demo simple, I'm basically using this to generate the embedding separately and sentences separately. All right. So now we are going to create the vector index. And again, I'm not going to invoke it because this roughly takes about 45 minutes and I don't want you to wait till that is done. So I have gone ahead and uploaded the file and I have created the vector search index. You can basically take a look at this. So now we are in the Google Cloud Vertex AI dashboard. And if you go to the vector search, you'll actually see that I have already created Lakeside Index and I have already deployed it as an endpoint. So you can see that there is a Lakeside Index with a specific endpoint. You can manage this either through the console or through the SDK or through the G-Cloud command line. Now I chose to do this via the SDK, but you can always instantiate it interactively by clicking on Create New Index. Okay, so that completes the first step, where we basically took our handbook, a PDF, and converted that into two files. One is a unique ID for each sentence and the embedding. The other one is same unique ID for each sentence, but the actual sentence. And we have gone ahead and turned this into a set of vector database entries in Vertex AI Vector Search. So now we have the data that's available within the vector index. So in the next step of this tutorial, we'll actually implement the RAG pipeline. So how do we retrieve the context? How do we embed that in the prompt and then send it to the LLM and make it respond to our questions? Stay tuned, and I'm going to show you the next part of this demo. All right. So in the previous step, we have seen creating the embeddings and the sentences files. So now let's actually implement RAG by performing the lookup, that is the retrieval and then generation. So we'll start by importing the modules. So here we don't need to deal with PDF because we are now looking up the vector database directly. So we'll import Vertex AI language models. We need the text embedding model. This is required because we need to convert the query into the same text embedding as the original embedding model. So they need to match. Otherwise, we're going to have very different dimension and it's not going to work. So we will first convert the input query into the same set of embeddings based on this model. Then we need AI platform because we are talking to the index endpoint, the deployed endpoint. And of course, we need Vertex AI to access the generative models and Gemini, JSON and OS to perform some housekeeping stuff. So let's go ahead and initialize the variables. So I'm going to retrieve my GCP project from environment variable, set the location to US Central, lakeside sentences.json. That is where we are going to perform the lookup locally. This can be even in a database, it doesn't matter. And the index name is Lakeside Index. And where is this index coming from? Well, let's go back to the Cloud Console. And if you look at the Vertex AI Vector Search, this is where we have the index and the index endpoint. All right. So we give that name. And then we're going to initialize the model and the vector index. So this is where it becomes interesting. So we'll first initialize the AI platform by giving the project name and the location. We'll also initialize Vertex AI to get the access to generative model, which is Gemini Pro. And then the index endpoint name is actually the ID that you see here. You look at the long number here, starting with 222 and ending with 016. This is basically the ID of the index endpoint. And we need this when we are initializing the endpoint. So we will grab that and then initialize the vector search. By the way, the Vertex AI Vector Search was called Matching Engine Index before it got renamed. So that's the reason why we still continue with that naming convention. So now this is initialized, and then we need some helper functions. Obviously, the first helper function is generating the text embedding. So it takes one or more sentences and then converts that into vectors. We need this to convert our query, the prompt, into the same embedding so that we can perform a lookup. And then load file. So this is very important. We load the sentences file locally into an in-memory variable called data. So this is where we do the mapping between the UUID of the embeddings that are returned and the UUID of the sentences living on our file system. Then we have the most important function, and this is actually called as generate context. Now, generate context takes the matching sentence IDs and the data that actually contains all the sentences, and it compares if the ID matches, and then it sends back a concatenated list of all the sentences. This is very critical because this is where the lookup takes place. So basically, the vector search will return us matching UUIDs, which are unique identifiers, and then we map them back to the sentences through this function called generate context. That's it. Now we are very close to performing the next step, which is performing a semantic search. So let's first populate data by calling load file and sentence file path. So this step will basically get us the data. So if you actually look at it, now this contains the ID and each of the sentences. This is what is stored in the data variable. Now, once that is done, we need to basically perform the query. So let's first initiate this query. What is the process for applying personal leave? So that is the query. And then what we do is we take this query and call generate text embeddings. So generate text embeddings will embed or basically encode this query into the same embedding model that we used for original vectors. So let's run this. So now we have two entries. One is the query that contains the prompt, and the other one is the query embeddings. Now, if you look at the query embeddings, it basically contains a long set of vectors. So that is basically the set of embeddings that we need. All right. So now with that in place, guess what? We are ready to basically perform, the, let me get this. So now we are ready to invoke okay. So now what we do is we are performing a query to find neighbors, find nearest neighbor. So that is the behind the scenes algorithm. Deployed index ID is the index name. The queries is basically the query embeddings, which we generated here. And we want to retrieve 10 neighbors. So let's go ahead and run this. Now we have the actual output. So let's go ahead and print response. Now, this is where it becomes very interesting. So what vector search comes back with is not exactly the sentences. It comes back with the unique identifiers, and it also has the distance. The higher this number, the closer it is to the query. And because we said 10, we get exactly 10 matches. Now, let's grab this ID, go to our sentence embeddings, and look at this. So now, unpaid personal leave. So because it has personal leave, it matches the query. Then if you look at one more string, let's do a search, and you can use your personal leave for reasons, blah, blah, blah. So what it basically does is it comes back with the IDs. And now our job is what we did with find, we have to do it programmatically. So that is the next step. So what we'll do is we will now perform we'll basically get all the matching IDs, okay? And we will send all the matching IDs from this response and the data, which is the in-memory representation of all our sentences, and this generates the context. Now, if you look at the context, there we go. Now, to make this easy to read, I'm going to print this. So, unpaid personal leave, you must request your personal leave at least 2 weeks in advance. So, basically, it extracted everything from this section, the leave policy section of the PDF. And now we are going to inject this context into the prompt and then make the actual inference. So now it's time for us to construct the prompt. So now I'm actually sending this prompt to Gemini. And what I'm saying here is based on the context delimited in backticks. And what am I delimiting in backticks? It is this variable called context. Answer the query. And what is the query? Well, the query is here, process for applying personal leave. So now we are going to final moment of truth. We are now going to invoke the chat completion endpoint of Gemini by sending the prompt. And this prompt is augmented prompt. It has the context, it has the query, and let's go ahead and run this. Now this is going to come back. Okay, so what was our query? Now the query is the process for applying personal leave. And now the response is you must request your personal leave at least 2 weeks in advance and obtain approval from supervisor and the HR department. Well, that's exactly what is mentioned here. You must request your personal leave 2 weeks in advance and all of that. Perfect. So let's try out a couple of more queries. So now, how many days of unpaid leave in a year? So if you look at this, you are eligible for 10 days of paid vacation. So, and you are eligible for up to 10 days of unpaid personal leave. So that's what is the query here. How many days of unpaid leave in a year? So let's run this query, generate the response. From the vector search, it comes back with 10 IDs, and then we load that. Let's print the context. Okay, now let's run this prompt and invoke the model. 10, exactly. Now it's precise. It just comes back with the exact number that we need. Now let's repeat this with a couple of more queries, right? So there is an interesting policy for this fictitious company called Lakeside Bicycles, and it says employees can sign up for online courses and they can get reimbursement up to $500 per employee per year, which is fantastic. So I'm a new employee and I want to understand what is the allowed cost of an online course. So let's run this query and let's invoke. Okay, perfect. $500 per year per employee. Now we are seeing RAG in action, powered by Vertex AI Vector Search and Gemini. So to wrap up, I want to bring back this slide here. Now, if you actually look at what we did, this is exactly the process we went through. So in our case, the Jupyter Notebook has been the chatbot. The search and retrieval is the code that we have written. The database is basically the Vertex AI Vector Search. The LLM is the Gemini LLM. Uh, and we have pretty much implemented all these 5 steps to get the exact responses. So that brings us to the end of this tutorial. I had a lot of fun building this. I hope you enjoyed it. In the next session of this series, I'm excited to bring you how to use LangChain with Gemini. So you have seen how to implement RAG. Now, what if we do the same thing with LangChain? So in the next session that I'm going to launch next week, I'm going to walk through how to implement RAG with LangChain and also how to, in general, use LangChain with Gemini. Stay tuned and don't forget to subscribe to my channel. I'll see you soon. Thank you.